Welcome back, everyone, to Synthesis Workshop. My name is Aidan Looby, and I am one of the editorial board members here on the channel. On today's episode, we are joined by Manuel Martin, who is an undergraduate student at Trinity College Dublin in Ireland, pursuing his BA in chemistry, and will give us an overview of catalytic carbonylation methods in the literature. Before I turn it over to Manuel, we hope that this episode encourages more undergraduate students to participate in Synthesis Workshop's video creation. There is a lot of organic chemistry to cover, and we hope to make room for everyone to contribute. Finally, make sure to like the video and subscribe to the channel as we continue to make more organic chemistry videos. It really goes a long way for us. Thank you again, and now I will turn it over to Manuel.
Thanks for the introduction. It's great to be here today. I'll be discussing catalytic carbonylation, an area with significant impact in both academic research and industrial applications. So here's a brief outline of the topics we'll cover today. First, we're going to begin by talking about the famous hydroformylation reaction, both the cobalt and rhodium-catalyzed hydroformylation. Then we're going to very briefly talk about the enantioselective versions of this reaction, to then talk about the Palladium-catalyzed carbonylation of organic halides, also some synthetic applications of these reactions. Then we're going to see the Pauson-Khand reaction and how this reaction is applied in total synthesis. Then we're going to see Carbonylative C-H activation, and finally we're going to discuss how to generate CO in and ex situ, which is very useful as well. So the first reaction we're going to talk about is the hydroformylation of alkenes, which is sometimes called the OXO process. It was initially discovered by Roelen. It is indeed a very important reaction industrially. This is a metal-catalyzed reaction in which an alkene reacts with hydrogen, gas and carbon monoxide, usually in very high pressures, to yield an aldehyde. As I said, it's very important. It's one of the largest volume reactions using homogeneous catalysis in industry, and is used to produce over 14 billion pounds of aldehyde per year. The mechanism for this hydroformylation, in the case of cobalt-catalyzed hydroformylation, begins with dissociation of carbonyl ligand from the cobalt catalyst, followed by coordination of the alkene, then undergoes CO insertion and hydride transfer, forming the alkyl chain, usually in the apical position, and then one of the CO ligands will then migrate to the alkyl chain. Then this undergoes oxidative addition, forming this octahedral complex, but also due to high pressure, this cobalt catalyst can also coordinate to another CO ligand instead. Then after reductive elimination, the aldehyde is delivered, but also following a parallel way, depending on how the hydride transfer is done, it can also lead to the branch product. One of the most important first developments observed was the addition of phosphine ligands, which increased the linear to branch ratio, very important especially for the phosphine ligands developed by Slaugh and Mullineaux at Shell improved this ratio. This is due to the electron donating property of the phosphine ligands, increasing the strength of the cobalt carbonyl bond due to back bonding, and that allows milder conditions, especially lower pressure. The size of the phosphine ligands affects the insertion direction of the alkene into the cobalt complex and the geometry of the intermediate, especially favoring the anti-Markovnikov selectivity. It is also worth mentioning that instead of carbonylation, you can get hydrogenation as a major side product. One of the most recent developments, actually from last year, was by Chem and co-workers, who reported a ligand-induced suppression of side products. As we saw before, one of the main side products can be hydrogenation using cobalt-catalyzed biphos ligands. This kind of ligand is known for its strong pi acceptor properties. So rhodium-catalyzed hydroformylation was also developed a while ago by Pruett and co-workers with triphenylphosphine ligands. This proved selective and active hydroformylation under 5-10 atmospheres of CO and hydrogen gas at 90 degrees Celsius. So these are milder conditions. However, as you increase the number of triphenylphosphine ligands that are in the catalyst, you can increase the selectivity, but also you will decrease the rate of reaction. The basic steps in the mechanism are quite similar to the hydroformylation using cobalt. This increase in selectivity is especially due to steric factors and the pi acceptor properties that this ligand has. It is worth noting that cobalt is vastly more abundant than rhodium, being like 100,000 times more common in the Earth's crust. So in diphosphine chelating ligands called the bite angle, this bite angle is basically the angle between the two MP bonds, and diphosphine ligands with a wider bite angles will allow the phosphine atoms to bind with both phosphorons in equatorial position. This di-equatorial arrangement will lead to higher linear to branch ratios. This is especially due to the transition states shown in the slide. If you have both ligands on the di-equatorial position, then that transition state, that last transition state, will kind of squeeze out the R group. This aliphatic chain will favor the linear instead of the branch product due to a steric hindrance. If you have instead one phosphine of the ligand in equatorial and the other on axial position, that won't interact that much with the R group. As you can see there, as you increase the bite angle, you will increase the Ni ratio. One of the most important developments that has been made is the enantioselective version of it. This is especially important for the synthesis of analgesic from vinyl arenes. One of the first proposed enantioselective hydroformulations was using RS binaphos ligand, which produces high enantioselectivity in the hydroformulations of vinyl arenes. These isomer ligands will lead also to higher Ni ratios. Then also 3,4-diazophospholane ligands have demonstrated good regioselectivity and enantioselectivity, but in this case with faster reaction rates than those achieved by the initial vinaphos ligands. More recent case also, the substrate scope is very broad. So many Palladium-catalyzed carbonylations of organic halides have been reported so far. The general catalytic cycle is oxidative addition of the organic halide, followed by a CO insertion, forming this acyl palladium intermediate. And then a nucleophile will attack to this carbonyl group, and it's usually needed as well a base to activate this nucleophile. One of the most robust reactions of this kind is the alkoxy carbonylation. Professor Heck, one big name in organic methodology, reported that this reaction can be performed under mild conditions. Nowadays it has a broad substrate scope. So one important synthetic application of oxycarbonylation is the total synthesis of spinosine A, the primary components of an insecticide with an excellent environmental profile. One of the steps of this proposed route is the carbonylative Heck microlactonization reaction, building both 5-member ring and the 12-member ring macrolactone in just one step, beginning with the oxidative addition of the palladium catalyst and the coordination of the alkene, followed by the migratory insertion, and finally the CO insertion, building both 12 and 5-member rings. For macrolactonization, they used tri-2-furyl phosphine ligand, optimal diastereoselectivity selectivity, then another palladium-catalyzed carbonylation of organic halides, another alkoxy carbonylation. It's a Semmelhack reaction. This is an intramolecular process, especially useful for lactonization, and it's a different type of alkoxy carbonylation as you can see. The palladium coordination to the alkene followed by hydride transfer, CO insertion, will lead lactone thanks to the OH attacking. A synthetic application of this Semmelhack reaction is the total synthesis of lambda-lecton A, reported by Jang and co-workers This is a modified late-stage Semmelhack alkoxy carbonylation to install a fused gamma-lactone system. As you can see here, they use urea ligands to be effective in preventing palladium precipitation, stable under oxidizing agents. Also, they avoid double bond isomerization. This was reported by Jang and co-workers as an effective ligand in palladium-catalyzed carbonylative reaction. Another important palladium-catalyzed carbonylation of organic halides is the Aminocarbonylation, especially useful for the preparation of amides, very useful in pharmaceutical industry. Mild conditions were observed initially for Aryl bromides and iodides. Then the work of another chemistry legend, Buchwald, provided mild conditions for Aryl chlorides. Also, reductive elimination. This is probably the reaction with greatest potential due to the wide range of derivatives that can be accessed from aldehydes. Especially the work of steel provided an effective hydride donor for mild conditions, which is tributyl tin hydride. A very famous reaction, carbonylation reaction, is the Pauson-Khand reaction. It's a reaction that was initially discovered by Dr. Khand when working as a postdoc for Professor Pauson. It's a formal 2+2+1 cycle addition and was initially discovered as an intermolecular reaction and as a stoichiometric reaction as well, but it has evolved to be a catalytic process, and the intramolecular version was reported 10 years later. But nowadays, as you can imagine, the intramolecular pKr has been studied in more detail, especially because it's one of the most efficient processes to construct cyclopentaenones. It is usually seen using a cobalt-catalyzed, but it can also be done using nickel, rhodium, or palladium. Sometimes one unsaturation is replaced with a carbonyl group. Then this is called the hetero-Pauson-Khand reaction. So the proposed mechanism from this species, which then undergoes alkyne insertion and ligand dissociation, forming the hexacarbonyl dicobalt acetylene complex. This undergoes a CO loss, forming the 16 electron complex, followed by alkene coordination, forming the 18 electron complex, and then this alkene and CO insertion, simply planar fashion, will lead to this other intermediate, which then will undergo CO insertion to the aliphatic chain. Then one of the cobalts will suffer a reductive elimination, and then the second reactive elimination will lead to the loss of the dicobalt hexacarbonyl complex and delivering this cyclopentanone. So the pre-association of the alkene and alkyne to the CO center, to the cobalt center, is highly ordered transition state. So, for example, if you are interested in increasing the rate, the LUMO of the olefin is lowered using strained alkenes, such as, for example, cyclopropene. So the binding constant of the alkene to the metal is going to be higher because the release of a strain during the coordination. So one of the most interesting applications of the pKr reaction is the scalable, stereo-controlled, and by the way elegant total synthesis of the oxynelamines A and B. This was reported by Bern and co-workers, where the Pauson-Khand reaction is one of the first steps forming the cyclopentane core. In this case, ethylene glycol assisted the pKr cycle addition. Apparently, after extensive experimentation, ethylene glycol and NMO dramatically improved the performance of the reaction. This is indeed interesting because the pKr reaction of unactivated alkenes is usually rare. This discovery is interesting. Then this regional selectivity arises because of the electron-donating NH-Boc group aligns away from the forming carbonyl group during the cyclization step. Also, some carbonylative C-H activation has been reported. So C-H activation will allow you to undergo a carbonylation without having to pre-install the halide. And although it's challenging, it is usually more efficient. Wang and co-workers reported the synthesis of pregabalin via directed CSP3H activation of alkylamines. which allows the formation of gamma-lactams and gamma-amino acids with tempo as the essential oxidant. CH activation also was applied to synthesize the Taylor-Seeding B4 core. Treatment with palladium chloride led to the formation of 6,1-DR mixture of diastereomeric palladicycles. The major diastereomer is the one shown in the slide. In the preferred transition state of the CH activation, the isopropyl group was occupying the pseudo-equatorial position. Palladicycles usually can be functionalized via either alkene and alkyne insertion or alkylation or CO insertion. Finally, another carbonylation applied to synthesis is for the scalable and concise synthesis of pancreatistatins via catalytic desymmetrization of benzene, reported by David Serla and co-workers. This photochemical carbonylation of the UV light, it's way different to the one presented so far. So this target belongs to a family of stereochemically alkaloids. It's with a potential anti-cancer activity. So the installation of the carbonyl bonds was in 2 steps, via bromination and then sodium tetracarbonyl cobalt-catalyzed aminocarbonylation under CO, atmosphere, and UV light. So this efficient route reported presents a rapid entry to the core of the target, seeing benzene as a substrate that can undergo 3-olefin type functionalization, which is a key simplification. So the proposed mechanism for this reaction is, first of all, the cobaltate anion that is representing the left coordinates to the Aryl halide. Then light promotes charge transfer of the donor-acceptor complex, and then loss of halide through an SRN1 mechanism leads to the radical pair, which then recombines in the solvent cage to form an Aryl cobalt species. Then this species undergoes CO migratory insertion, generating the acyl cobalt, which is then substituted by the deprotonated amine, which acts as a nucleophile, delivering the products. Another recent development is the carbonylation enabling the Aryl migration. It's a visible light as well induced carbonylation, which then triggers a radical rearrangement. So basically the CO insertion step is the key element for functional group migration, and that can lead to a series of 1,4-dicarbonyl compounds that were synthesized in this paper by Wang and co-workers. Further conversion indicates the big synthetic potential to reach many targets. So we've been talking about carbonylations and all of them needs handling carbon monoxide. So there are ways to do carbonylation without having to handle carbon monoxide, which usually requires either specialized equipment or dangerous, of course not non-recommendable installations. One of the most famous alternatives proposed is the development of a 2-chamber reaction, which is called the CO-ware, and they also reported the 2 stable and solid CO releasing molecules. So these molecules will release CO after activation with palladium or fluoride addition, and the carbon monoxide was shown to be released in a quantitative way, as demonstrated due to the high yield when a limited amount of acid chloride was applied. Finally, another work reported for, in this case, carbon monoxide generated in situ is by Holt and co-workers using chloroform as a precursor reagent, also useful when forming isotopically carbon-13 labeled amides. So in this work they describe the conditions for the rapid hydrolysis of chloroform to carbon monoxide using cesium hydroxide. So this was basically through the deprotonation of chloroform and alpha elimination leading to the dichlorocarbon, which then will coordinate to palladium and then will decompose to release the CO, the carbon monoxide. But this is important. This method is only applicable for palladium-catalyzed aminocarbonylations. Well, I hope you have enjoyed watching this video a lot. And I just wanted to say thank you to all the Synthesis Workshop videos team, and especially to Matt, who has been guiding me throughout this whole production. And also, I would like to encourage any individual, but especially undergrads, to become part of this project, because I haven't seen any undergrads, and I feel like it's a very rewarding experience. Thank you so much. Take care.